Next case is the spherical capacitor. We have two massive conductors, inner solid sphere and the outer hollow sphere. The inner sphere has the potential of plus 1 volts and the outer sphere is grounded. There is the air between the spheres, so this construction is a spherical capacitor. Our task is to calculate the capacitance of this capacitor. There is the analytical solution and you can see equation on your screen, and following this equation the capacitance should be 22.2 pF. We will simulate this case in QuickField and find the capacitance there. There is no electric field inside conductors, so there is no need to include the conductors in our simulation model. We need to include only the dielectric media, which is air in our case, and the conductor's faces. We will assign plus 1 volt electric potential to the inner sphere face, and we will assign 0 electric potential to the outer sphere face. Inner sphere would be positively charged and the outer sphere will be negatively charged, and the capacitance is the ratio of electric charge to the potential difference, which is 1 volt in our case. So all we need from QuickField is to find the electric charge. Okay, I start QuickField now and create new problem. Spherical capacitor. Next. The problem type is Electrostatics and the model class is three-dimensional import. Okay. Here is the problem tree on the left, and on the right you can see the geometry model editor window. I will import the geometry model from the step file. Here it is. So we have two bodies here, but I can see only one. Let's select everything and make it transparent. Right click transparent. Now I see there are two spheres, one inside another. Well, let's make them opaque again. Now we should assign labels. Labels are used to distinguish geometric objects from one another, and labels are used to assign physical properties to geometric objects. To assign a label you should first select an object. I move the mouse over the object, it is highlighted, then I click it. It is green now, it is selected. What is selected you can see here in the properties window. You see the face is selected. Only one face. This is the grounded surface of the outer massive conductor. So I will assign the name grounded. To select the body you should click the face again. Now the face is selected, and if I click the selected face I will select the body that's located behind this face. Click it. Now you see the color has changed, and in the properties window you can see that the body is selected. This is the air. To see the internal sphere I will hide the air block. Right click, hide. This is the internal conducting sphere. I will select the surface of the sphere, click it, and assign the label +1. Remember, the internal sphere is made of conducting material, so there is no electric field inside this sphere. So there is no need to assign label to the sphere itself. Only the surface of the sphere has the label. Now let's assign physical properties to these labels. I will unhide all bodies, make this body transparent, so you can see better what is selected. +1. This is the face of the internal sphere. It has the electric potential 1 volt. Grounded. It is the surface that belongs to the outer sphere. It has the electric potential 0 volt. For the air I specified the electric permittivity of 1. Okay. Now let's build the finite element mesh. You can do this in 3 stages. First you build the mesh on the edges, then you build the mesh on the faces, and the last you build the mesh in the volumes. Everything is ready, we can run the simulation. Yes, save simulation files. Now we can take a look at the result. Here we can see the air block external surface. To look inside you can hide objects or you can use the cut by plane tool. I will hide the cut plane. Now you can see what it is inside the spherical capacitor. This is the electric potential distribution, and I can adjust the picture and switch on the electric field strength distribution. And the field distribution looks strange. You see, our sphere is symmetrical and the field distribution should be symmetrical too, but I can see these colored spots randomly placed on the surfaces. The reason to the poor accuracy is the finite element mesh low quality. QuickField utilizes finite element mesh method. In each element the field distribution is considered to be linear. And we know that in the spherical capacitor electrical field strength is in inverse proportion to the distance squared. Let me show you. I will switch on the two-dimensional section, add the contour here, from here to here, and take a look at the field distribution along the contour. Strength. You see the straight line instead of the smooth curve with the inverse proportion to the distance squared. Let's take a look at the finite element mesh. I'll switch on the mesh here, half clip. There is only one layer, linear dependency instead of the squared. Of course we get the poor accuracy in this case. To get better accuracy, let's adjust the finite element mesh. I open the geometry model. You see, QuickField chooses finite element mesh size depending on the geometric object size. The larger the object, the larger the element size. QuickField doesn't know in advance what will be the field distribution, but we know. So let's change the spacing. I select everything and change the spacing to manual. And here you should type in the value. For example, 0.05 meters, 5 centimeters. Let's build the mesh again and run the simulation. Now again I will use the cut by plane tool and switch to the electric field strength. Now that's better, but still we see the spots. Okay, let's go to the geometry model again. Select everything. Spacing value 0.02. Build the mesh, run the analysis. Again I will use cut by plane. It looks better now. I will again switch to the two-dimensional section, use the contour tool. Now let's take a look at the XY plot. And the electric field strength. Now this is the dependence we were expected to get. It is not the straight line, it is in inverse proportion to the distance squared. But what if we didn't know in advance the analytical solution? What should we do then? How to make sure that the solution is accurate? Well, that's easy. You just build the denser mesh and compare the results. Well, it's not convenient to compare the plots. Let's compare some integral values. So I go back to the three-dimensional results window. Remember, our task was to calculate the capacitance. We know the potential difference. It is 1 volt. So we need to find the electric charge. Well, that's easy. I will switch off the cut by plane tool, hide the air block, and now we can see the internal sphere. To calculate the charge, I should select the surface of the massive conductor. I can see the surface. I can use the integral tool and select this surface. Now the electric charge is 1.8 times 10 to the power of minus 11 coulombs. And if I divide this charge by the potential difference, I will get the capacitance, which will be 18.65 picofards. And the analytical solution gives us 22.2. Well, 1865 in QuickField and the analytical solution 22.2. The difference between results calculated in QuickField and the analytical solution is 16%. Let's again adjust the mesh and see if we can get better accuracy. Open the geometry model, select everything and set the spacing value to 1 centimeter. Build the mesh again and run the analysis. Okay, again I will hide the air block and use the integral tool to find the charge. 20.41, it was 1865. If I divide now 20.41 by the analytical value 22.2, now the difference between the result calculated in QuickField and the analytical result is only 8%. Now let's stop for now and use other ways to verify our results. Our internal surface has positive electric potential, so the charge should be positive. Let's verify it. Indeed, the charge sign is positive, and the negative charge should be stored on the external hollow sphere. Let's verify this. I will unhide all and click here, and the electric charge is positive, but it should be negative. What we see now is the air block, and what we have selected now is the air block face, but there is no electric charge stored in the air block. The charge is distributed along the face of the conductor, but the outer sphere conductor is not included in the model. Let's take a look at the geometry model. I will use the cut plane tool here. Now we have the conducting sphere inside and we have the hollow conducting sphere outside. And to measure the electric charge on the conducting sphere surface, we should click it from here, from that side. If we click from this side, we will select the air block face. To select the conductor face, we should take a look at the conductor and click from this side. Try to do it and hide the air block. You will see that there is no external boundary. That's because we do not have the external sphere in our geometry model. Well, I have another model with the outer sphere as a solid shell. So let's go to the geometry model editor window and import the other step file, spheres 3. Again, I will make this transparent. Now you see there is the internal sphere, the air block and the external sphere. Made this opaque again and assign the labels. This is the conductor. There is no need to assign label to the body. Simply hide it. Now this face has 0 electric potential. Click again to select the body behind this face, and this body is the air. Hide. Now this face has the electric potential of +1, and there is no need to assign the label to the body because this is the conductor and there is no electric field inside conductor. So let's unhide all and build the finite element mesh. Oh, remember, we should adjust the mesh spacing to get accurate results. I select everything, switch to the manual spacing and type in 0.02. Now let's build the finite element mesh on faces, on volumes, and run the analysis. Let's take a look at the result. Again, I will use the cut byte plane and I will hide the air block. You see there is no more dielectric here, there is no air here. There are only conducting objects. If I select the surface of the conductor, I will calculate the charge stored on the conductor. Inner sphere should have the positive charge and the outer sphere should have the negative charge. For example, I will click the grounded and the face is selected, go to the integrals, and here is the charge. Again, let's compare the charge value with the analytical one. It is 23.8, but it should be 22.2. The difference is 7%. And if you need better accuracy, just go to the geometry model and adjust the spacing value here. Now that's all. We have simulated spherical capacitor, calculated the charges. All the values and pictures you get here you can copy and paste in the report. You can adjust the field picture, you can hide and unhide objects. You can use the two-dimensional section window and build contours here, and then see the field distribution along the contour lines on the XY plot or in the table. You can adjust the table window, choose which values to display. You can adjust the tabulating steps, for example 2 millimeters. You can save table as a file, or you can copy all the data from the table and paste them, for example in Excel, and then build the plots here. The same you see in QuickField. You can find the simulation files on our website. Here is the page, and here is the download link. In fact, the problem we have simulated could be simulated as a two-dimensional one, and you can find the two-dimensional solution here to end the video.